What if I told you that the soap in your bathroom might have once fried your chicken nuggets? Across the world, used cooking oil is being converted into soap, saving millions of gallons from sewers and turning waste into an everyday product. Every night, as restaurants close their doors, they're left with a common problem: gallons of used cooking oil that's too degraded for further food preparation. This murky liquid, once golden and clear, has transformed through hours of frying into a dark substance filled with food particles and chemical changes that make it unsuitable for cooking. In the past, this oil was viewed purely as waste, a problem to be solved, often at the restaurant's expense. The evolution of the used cooking oil market represents one of the most significant shifts in restaurant waste management of the past decade. 15 years ago, restaurant owners typically paid disposal companies to haul away their used fryer oil. Today, that same oil has become a sought-after commodity in a competitive marketplace where collectors actively bid for access to restaurant waste. This dramatic reversal has transformed oil disposal from a cost center to a potential revenue stream for food service businesses. Behind this transformation lies a network of specialized collection companies, forming the crucial first link in the recycling chain. These companies distribute custom storage containers to restaurants, from drums for smaller establishments to larger containers for high-volume operations. These containers feature leak-proof seals, heat resistance for hot oil, and filtration screens for food particles. Take Mario's Pizzeria in Chicago, for example. Every Tuesday morning, collection driver Ramon arrives just after the breakfast rush. He connects his truck's hose to the restaurant's oil container behind the kitchen, extracts 75 gallons of used oil from their busy weekend, and leaves a receipt showing the $22.50 Mario will receive as credit on next month's statement. The entire process takes less than 10 minutes, allowing Ramon to service dozens more restaurants before his shift ends. The economic incentives driving the system continue to evolve. Collection companies typically offer tiered payment structures based on volume and quality. Small cafes might receive 15 to 25 cents per gallon, while high-volume operations with better oil management practices can command 30 to 40 cents per gallon or more. These payments are often structured as monthly rebates, creating a reliable supplemental income for restaurants that properly manage their oil. The system naturally encourages better handling practices. Restaurants learn quickly that excessive water contamination or food waste reduces their oil's value. Many collection companies provide training materials to help restaurant staff properly filter oil between uses, extending its cooking life while ensuring higher quality when recycled. The environmental impact of these practices is substantial. Proper oil collection prevents improper disposal in drains or landfills where it can contaminate water supplies or create waste management challenges. Instead, this organized collection system diverts millions of gallons into sustainable recycling channels. The collected oil varies remarkably in quality and composition. Quick service restaurants primarily frying potatoes typically produce lighter, less contaminated oil than full-service establishments using the same oil for multiple foods. Seasonality affects quality too. Summer months with higher humidity often result in higher water content, while winter collections contain more solidified fats. In metropolitan areas, a single collection company might service thousands of restaurants, gathering millions of gallons monthly. Technology continues to enhance the system, with storage containers featuring sensors that alert collection companies when containers reach capacity, and GPS-optimized routing ensures trucks take efficient paths between collection points. Through this sophisticated network, what was once a disposal problem has become a valuable resource, creating economic benefits for restaurants while supporting environmental sustainability through the redirection of a once wasted material. Those tanker trucks full of used cooking oil arrive at factories carrying a substance that's more waste than resource, until it passes through a transformation most people have never witnessed. What these facilities receive bears little resemblance to cooking oil as consumers know it. Instead, it's a murky, dark liquid laden with particles from thousands of meals, sediment from restaurant fryers, and a cocktail of chemical compounds created during repeated heating cycles. The purification challenge facing industrial soap manufacturers is monumental. Unlike home soap makers who might filter small batches through coffee filters or cheesecloth, factories must process thousands of gallons daily while removing an array of contaminants: microscopic food particles, water content, free fatty acids, trace metals from cooking equipment, and debris that found its way into collection containers. Think of it as similar to water filtration but on an industrial scale. Your home filter removes impurities from drinking water, while these facilities clean thousands of gallons of complex waste oil. The filtration process begins with simple but effective mechanical screening. Massive stainless steel screens catch the largest debris, from accidental utensils to sizable food chunks. From there, the oil moves through progressively finer filtration systems, each designed to trap smaller particles. The most advanced systems capture contaminants measuring just a few microns, invisible to the naked eye. Temperature control is critical throughout this initial stage. Engineers heat the oil to precise temperatures that balance competing needs: warm enough to flow freely through filtration systems, yet not so hot that it degrades the molecular structure needed for quality soap. This delicate balance requires constant monitoring, with temperatures maintained in specific ranges to optimize efficiency while preserving oil quality. With larger particles removed, the next challenge becomes eliminating water and separating heavier contaminants. This is where centrifugal separation technology becomes essential. Industrial centrifuges spin the oil at high speeds, creating forces hundreds of times stronger than gravity. Heavier elements like remaining solids and water are forced outward and removed. Modern centrifuges process hundreds of gallons hourly, achieving separation impossible through gravity alone. Water removal is particularly crucial because even small amounts of moisture can impair the coming saponification reaction. To address this, facilities employ vacuum dehydration systems that create low-pressure environments where water evaporates at lower temperatures. These systems reduce moisture content to less than 0.1%, ensuring optimal soap production. Some contaminants resist mechanical filtration entirely, requiring chemical purification methods. Facilities introduce materials like bleaching clays and activated carbon that work at the molecular level, absorbing pigments, persistent odors, and organic compounds that mechanical systems cannot capture. After sufficient contact time, these absorbents are removed through additional filtration, taking their captured impurities with them. The combination of these techniques transforms waste into a remarkably clean, consistent base material. The visual difference is striking. Oil that entered as a dark, cloudy liquid emerges with dramatically improved clarity and significantly lighter color. Even more impressive is the transformation at the molecular level, where contaminants have been reduced to fractions of a percent. Quality control technicians regularly test the purified oil, measuring parameters like free fatty acid content, moisture levels, and impurity concentrations. These tests ensure that only oil meeting strict standards moves to the next production phase. Any batches falling short are routed back through appropriate purification stages until they meet quality thresholds. A commitment to consistency essential for reliable soap production. That meticulously purified oil now stands at the threshold of its most dramatic transformation yet. Within massive stainless steel vessels, molecules that once made surfaces greasy will soon be restructured into ones that remove grease, all through a precisely controlled chemical reaction that dates back thousands of years, yet requires modern engineering to execute at industrial scale. The scientific name for this molecular metamorphosis is saponification, the fundamental chemical process that transforms ordinary fats and oils into soap. At its core, saponification is an elegant chemical dance between two partners, the purified cooking oil and an alkali substance. Inside these industrial reaction vessels, the oil molecules encounter either sodium hydroxide or lye or potassium hydroxide. This choice fundamentally determines the final product's characteristics. Sodium hydroxide produces hard, long-lasting bar soaps for general cleaning, while potassium hydroxide creates softer, more water-soluble products ideal for liquid soaps and shaving creams, with a creamier, more luxurious lather. The chemical transformation occurring inside these vessels resembles a perfectly choreographed ballet. Each oil molecule takes its position, breaks apart, and reconnects in an entirely new configuration. The result is a soap molecule with a fascinating dual personality, one end hydrophilic, while the opposite end hydrophobic. This unique structure explains soap's cleaning magic, with the oil-loving end attaching to grease, while the water-loving end makes it possible to rinse everything away. Executing saponification at industrial scale requires extraordinary precision. Computers analyze each oil batch's exact composition before it enters the reaction vessel. This analysis determines the precise amount of alkali needed. Too little leaves unreacted oil that reduces cleaning power, while too much creates harsh soap that irritates skin. With calculations complete, measured quantities enter the reaction chamber, where transformation begins. The vessels themselves are engineering marvels designed specifically for this molecular ballet. These industrial chambers feature sophisticated temperature control systems, maintaining optimal conditions between 80 and 100 degrees Celsius. Temperature regulation is crucial because saponification generates substantial heat on its own. Without careful management of this thermal energy, the reaction could overheat, compromising the final product's quality. Throughout the process, advanced computer systems continuously monitor multiple parameters. High-precision sensors track everything from viscosity to pH, while automated systems adjust mixing speed and temperature. The mixture visibly transforms as the reaction progresses, evolving from a thin liquid to a thicker, opaque substance. Physical evidence of the molecular transformation underway. Many manufacturers incorporate superfatting, adding refinement to the finished product. This technique calculates a specific amount of extra oil beyond what will react with the alkali. This excess oil remains in its original form within the soap, providing moisturizing properties that benefit the skin. Superfatting allows manufacturers to fine-tune their soap's qualities for different skin types and preferences. The time required for complete saponification varies based on batch size, oil composition, and temperature. In most industrial settings, the reaction reaches completion within several hours, remarkably fast compared to traditional methods. Throughout this period, computer-controlled systems continuously adjust conditions to ensure optimal reactions. For those familiar with the grimy, particle-filled used cooking oil collected from restaurants, this transformation seems almost magical. A substance once synonymous with dirty becomes something designed specifically to make things clean. Yet there's nothing supernatural about this change. It's entirely explained by the rearrangement of molecules during saponification, creating structures with properties utterly different from their origins. The chemical symphony may be complete, but our soap is still far from being the solid product you recognize in your shower. What emerges from the saponification process is a hot, flowing substance that bears little resemblance to the firm bars we associate with soap. This molten mixture now enters perhaps the most visually dramatic phase of production, where timing precision can make the difference between perfect bars and ruined batches. As the hot soap flows from reaction vessels, it enters specialized finishing equipment, where manufacturers introduce the elements that define the final product's character. Here, colorants transform plain bases into vibrant hues, while fragrances, from delicate florals to robust earthy scents, blend into the mixture. Moisturizers, exfoliants, and specialized cleansing compounds join the formula, each integrated to enhance specific properties without disrupting the soap's fundamental structure. This customization stage transforms the basic soap into something uniquely appealing to consumers, where each addition contributes distinct qualities to the final product. Production supervisors monitor this transformation with vigilant precision. The customization window requires exacting temperature control. Too cool and the mixture becomes unworkable with potential structural weaknesses. Too hot and solidification time extends, creating production bottlenecks. This delicate balance explains why manufacturing facilities maintain such precise environmental controls, essentially sculpting a liquid masterpiece before it can set into its final form. Industrial facilities employ a continuous pouring system that channel the customized soap mixture into massive mold frames, creating enormous soap slabs that dwarf artisanal productions. These industrial-scale formations span several feet in width and extend dozens of feet in length, creating solid soap highways that will eventually become thousands of individual bars. These enormous slabs then enter climate-controlled curing rooms where specialized sensors continuously monitor and adjust temperature and humidity levels. This precise environmental management facilitates proper hardening and water evaporation, crucial to the soap's ultimate quality and performance. Modern manufacturing has dramatically accelerated the curing phase. While traditional soap making requires 4 to 6 weeks of patience, industrial techniques using vacuum chambers and controlled airflow systems have compressed this timeline to approximately 7 to 10 days without sacrificing quality. This acceleration enables continuous production cycles that historical soap makers could never have imagined. During curing, complex reactions continue throughout the slab. Remaining alkali continues reacting with oils, excess water evaporates, and the crystalline structure develops. This microscopic architecture gives the finished product its strength, longevity, and resistance to premature deterioration when exposed to water. Quality control technicians conduct rigorous testing to determine when the soap has reached optimal condition. They assess hardness levels, measure moisture content, and verify pH values to ensure the soap will be gentle on skin. These evaluations pinpoint the perfect moment for transformation from slab to individual bars. This transformation happens with remarkable efficiency. Automated cutting equipment featuring high-precision wire or blade systems process thousands of dimensionally identical bars per hour. These cutting systems maintain perfect alignment across large cutting surfaces, ensuring consistent packaging and consumer experience. For consumers who only see the finished product, this industrial-scale production would be astonishing. The journey from flowing liquid to perfectly formed bar involves sophisticated engineering solutions developed through decades of manufacturing innovation. The controlled environments, precision timing, and automated systems have transformed a time-consuming craft into a high-volume industrial process, meeting global demand while maintaining the essence of what makes soap such an essential part of our daily lives. Those perfectly formed bars now face their final challenge: convincing consumers to embrace a product made from what was once considered waste. Behind the scenes, packaging lines operate at mind-boggling speeds, with some facilities wrapping up to 300 bars per minute. This remarkable efficiency serves as a critical hygiene measure. The automation minimizes human handling throughout the packaging process, significantly reducing contamination risks while maintaining the sterile environment essential for personal care products. The economics of this high-speed automation explains why recycled soap can compete price-wise with conventional products. Without these efficient systems, cost of producing recycled soap would likely be prohibitively expensive for mainstream consumers. The packaging equipment represents decades of engineering refinement, with computerized systems that detect and remove imperfect bars before they're wrapped, ensuring consistent quality control throughout the production run. Speed represents just one aspect of modern soap production. Today's manufacturers face growing pressure to align their packaging choices with the environmental benefits of their recycled products. This has sparked innovation across the industry, with many companies transitioning to partially or fully recycled paperboard for their boxes and labels. Picture a bar of soap nestled in packaging made entirely from reclaimed materials, creating a beautiful symmetry where both product and package tell a complete, sustainable story. Forward-thinking manufacturers are exploring biodegradable films to replace traditional plastic wraps around individual bars. Some pioneering companies have developed soap boxes made from plantable seed paper that can be placed directly in soil after use, allowing consumers to grow wildflowers from what would otherwise be discarded. Others offer wrappers created from fully compostable materials that break down completely in home composting systems within weeks. These packaging innovations create closed-loop systems where resources continually circulate rather than becoming waste. When both the product and its packaging derive from recycled or renewable sources, the environmental impact improves dramatically. For eco-conscious shoppers, this approach transforms made from waste into a compelling selling point. As one customer recently shared, "I love knowing that my daily shower helps solve environmental problems instead of creating them." The environmental benefits extend beyond innovative packaging. By diverting used cooking oil from improper disposal, manufacturers prevent water pollution that would harm aquatic ecosystems. A single large soap factory can transform up to 200,000 gallons of used cooking oil daily, oil that would otherwise form oxygen-blocking barriers on water surfaces when improperly discarded. This massive diversion represents one of industrial recycling's most complete success stories, transforming a waste product with negative value into something consumers actively seek. The recycling process simultaneously reduces landfill demands and decreases market pressure for virgin palm oil, an ingredient commonly used in conventional soap manufacturing, linked directly to tropical deforestation. Once packaged and ready for distribution, recycled soap products flow through various channels to reach different consumers. Some manufacturers focus on bulk institutional sales to hotels and hospitals that benefit from both cost savings and environmental messaging. Others create branded retail products positioned at various price points, from budget-friendly supermarket options to premium offerings in specialty eco-conscious stores. This diversified distribution strategy ensures recycled soap reaches the widest possible audience, maximizing environmental impact through broad adoption. Each channel requires tailored messaging to effectively communicate the product's unique origins. While institutional buyers focus primarily on performance metrics and cost efficiency, retail packaging balances transparency about ingredients with appealing design elements that overcome any hesitation about using products made from reclaimed materials, making sustainability an everyday choice rather than a specialty interest. What we've witnessed throughout this journey is a perfect embodiment of circular economy principles in action. By transforming waste cooking oil into soap, manufacturers have created a complete loop where one industry's byproduct becomes another's raw material. This transformation represents a paradigm shift in how we view waste. Every bar of recycled soap reduces pressure on natural ecosystems while solving waste management challenges. These soaps close the loop of nature's design, telling a compelling story of environmental stewardship. With each purchase, you participate in this circular journey. Consider how you might embrace similar sustainable practices in your daily life, because yesterday's waste truly becomes tomorrow's solution.